Hi everyone, this is lecture video 22 and we will cover monotonic functions and first derivative test in this section. While sketching the graph of a differentiable function, it is so useful to know where the function is increasing and where the function is decreasing. So we give a very useful quick way of testing this here in this box. If your function is positive, then if the first derivative of the function is positive, then the original function f is increasing, okay? So if the first derivative is positive over some interval, your function will be increasing over that interval. If the first derivative is negative, then f will be decreasing over that interval. This is the very quick and useful way of detecting whether your function is increasing or decreasing. Okay, let's quickly apply this tool in the previous example. We have a function here, f of x given, and we want to find the critical points of it. And then after identifying the critical points, we will find the intervals over which f is decreasing and f is increasing. Okay, first critical points, then we will find the intervals where f is decreasing and increasing. So how do we detect critical points? We will remember that critical points are the points at which your function, the first derivative function is 0 or first derivative is undefined. This is how we find critical points. So let's compute the first derivative of this f of x. It is by using differentiation rules. It is computed like this. And then you can rewrite it like so. From here, if you find the roots, you will obtain x equals 2 and x equals minus 2. Is there any point where f prime is undefined? F prime x is undefined? No, there is no such point, right? Because this is a polynomial, you can evaluate a polynomial at every real number, so no points coming from here. Meaning that these two are only the critical points of this function. Critical points are x equals 2 and x equals minus 2. Now, we will try to find the intervals over which first derivative is positive and first derivative is negative to decide the increasing, decreasing intervals of the original function. For this, you can create a sign table for the first derivative function. What is a sign table? You will first insert these roots to your table, okay, minus 2 and plus 2. At these points, you know that first derivative is 0, and between minus infinity to minus 2 over this interval, look at your first derivative function. Is it positive or negative? You can just pick up a number from this interval, insert it to here to decide. You will find always positive values for the first derivative function. Between minus 2 and plus 2, you can just insert 0 here and see it takes negative values. And then after the point 2, over this interval, just pick 3, insert here, and we will see that first derivative function is always positive there. So this is how you create your sign table. And then by looking at the signs of your first derivative function, you can decide whether f is increasing or decreasing. Since the first derivative is positive over the interval minus infinity to minus 2, first derivative is positive, so function is increasing. Negative, function decreasing. Positive, function is increasing, okay? We can check these facts, we can check this information, verify it from the graph. Okay, this is the first interval from minus infinity to minus 2, it is here. And you can see that your function is increasing over that interval. Next, over this interval, minus 2 to 2, it corresponds to here. Your function is supposed to be decreasing, and yes, it is a decreasing function over there. And over the last interval, from 2 to plus infinity, which is here, your function is supposed to be increasing. Let's check. verify, yes, our function is increasing over there. So this is what we call as the first derivative test, and we use it to identify the intervals over which your function is increasing and decreasing. How we do that? We just find the sign of the first derivative function over that intervals after computing the critical points, of course. Okay, let's move on. So we have this general diagram here. It gives us the general cases where we may have first derivative positive, negative. Okay, we will analyze it in details. So here, first of all, we need to emphasize that the first derivative changes sign at a critical point where a local extremum point occurs, okay? This is the important fact. And let me show you the details of this diagram for you. For example, here we have first derivative 0, right? Because of this horizontal tangent. And at this point C1, what happens? First derivative 0, before C1, look at your function. Your function is increasing, right? That's why first derivative should take positive sign over there. And after C1, first derivative is still increased, still positive. So your function is still increasing there. So here, first derivative does not change its sign. That's why you don't have a turning point like this. Your function keeps increasing there. And there is no local extremum point here. Okay, I can also create the table for this point. So we are interested in the point C1. Look at the signs of the first derivative function. Both positive. Before it is positive. After C1, it is positive. At C1, first derivative is 0. So you see, first derivative doesn't change its sign. Okay, so your function keeps increasing and increasing. Okay, let me write first. Okay. First derivative does not change sign. Its sign. If the first derivative is positive, meaning that your function keeps increasing and increasing there. And let's look at C2 point now. At this point, we have horizontal tangent, meaning that you have first derivative 0. Before C2, your function is increasing. After C2, your function is decreasing, right? Here it is increasing. Here you have decreasing function. That's why at C2, you have such a local maximum point, okay? Local maximum point. And at this extremum point, which is a local max, you see that first derivative changes its sign, okay? Whenever first derivative changes its sign, you will have local max or local min. If it does not change the sign, which is the case at C1, there will be no extremum points there. Okay, what happens at C2? Let's create a diagram together. At the point C2, first derivative function, okay, it is 0. Before C2, your function is increasing. That's why first derivative should be positive. After C2, your function is decreasing. That's why your first derivative should be negative. You see, first derivative changes its sign. So before C2, your function is increasing. After C2, it is decreasing. And this suggests what? Increasing and decreasing, meaning that there has to be a turning kind of point at C2. So x equals C2 is a local maximum point, right? It's a local max. So to have local max or local min, first derivative should change its sign, okay? This is the important thing here. First derivative changes its sign. That's why you have a local max or min. But here, in the previous case, it does not change. That's why no local extremum points there. Okay, let's continue our analysis with C3. what happens here? Before C3, your function is decreasing, so first derivative is negative. After C3, it is increasing function, so first derivative should be positive. That's why here at this point, C3, you will have a local minimum point. Okay, so let's create the diagram also for that. This is a local minimum point because first derivative changes its sign there. Okay, like this. Before that, first derivative is negative. After C3, it is positive. At C3, it is 0. First derivative is 0, so this is a critical point. And what happens to your original function? That negative means decreasing, positive means increasing. That's why you will have this kind of behavior there, showing us that C3 point is a local minimum point. And the important thing that I need to emphasize, that at this point, first derivative changes its sign, okay? And then we can also look at C5. Here at C5, what happens? First derivative is 0 again. Similarly, your function is decreasing before C5 and it keeps decreasing after C5. That's why first derivative function is always negative. Decreasing means first derivative is negative. It does not change its sign. So does not change sign. That's why there is no local extremum point here, okay? And the similar case happened here, remember? At the first point, again, first derivative positive, positive doesn't change sign. That's why there is no local extremum point there, okay? So to have a local, what is the lesson here? To have a local maximum point or a local minimum point, you first derivative need to change its sign from positive to negative, or negative to positive. If positive to negative, you have a local max. If negative to positive, look, you have a local min, okay? So let me also show you one more point here, which is C4. What happens at C4? At C4, there is a corner. That's why first derivative is undefined there. Since there is a corner cusp-like point at C4, but it is still a local maximum point. Since it is the highest point, then you call that particular local max as the absolute maximum point. Okay, let's move on. The phenomena that I explained here in terms of the first derivative, so if it changes sign, you have a local max or min. This tool is called the first derivative test, okay? If f prime changes sign from negative to positive, which is the case here, you will have a local minimum point. If it changes sign from positive to negative, like this one here, you will have obviously a local maximum point there. If it does not change sign, if it is positive, positive, or negative, negative, like we have at C5, there will be no extremum point there, okay? So local max, local min, or no extremum points, no local extremum, you can detect this by using first derivative test. Okay, let's move on. Here is the example for you. Our function is given with this expression. We want to find the intervals on which f is increasing, decreasing, then we want to find the local and absolute extreme values of this function. First of all, you start by computing the critical points. Okay, that's why we start by computing the first derivative. Be careful, this is a product function, okay? That's why I need to apply the product rule. Derivative of the first component is 2x times the second component plus first component stays the same times the derivative of the second function. And then rewrite this first derivative as this one. So what we have, e to the power x, x minus 3, sorry, x plus 3, x minus 1, I guess. So this is your first derivative function. Let's equate it to 0 to see critical points. X equals minus 3 and x equals 1 are the critical points here. Any function where f prime is undefined, let's check. There is no such point. That's why this is the complete list of critical points. Okay, now by using these critical points, I will create a sign table. Why I am doing that? To detect where f is increasing and where f is decreasing. So put these points in your diagram, minus 3 plus 1. First derivative function is 0 at minus 3 and plus 1. Before minus 3, try to detect the sign of your first derivative function. If you insert here real numbers over this interval, for example, minus 4, you can just try. You will see that first derivative function gets positive values. And over this interval from minus 3 to 1, just pick the value 0. 0, if you insert 0, you will see that negative values appear. And after 1, you can choose to insert and see that first derivative function gets positive values from 1 to plus infinity over this interval. So these are the signs of the first derivative function. Next, you can write where f is increasing, where f is decreasing. So plus, first derivative is plus, positive. So function is increasing, decreasing, increasing, right? So what happens at x equals minus 3? Is it a local max, local min, or there is no extreme point there? Let's try to answer this question. So your function is increasing till minus 3, and then it starts decreasing like this. So the behavior is kind of like this. That's why at this point, x equals minus 3, you have a local maximum point. And here what happens, your function is decreasing and then it starts increasing. That's why this is the local minimum point now, okay? We can verify these facts by looking at the graph. Over this interval from minus infinity to minus 3, your function is supposed to be increasing. Let's see, minus infinity to minus 3 is this interval, and yes, your function is increasing over there like that. And then from minus 3 to 1, it is decreasing. Let's see, from minus 3 to 1 till here, you see your function is decreasing function, and the last interval is from plus 1 to plus infinity. It should be increasing. Let's check. You see, this is an increasing function over this interval. Okay, so also from the graph, you see that this point is a local maximum point. This point is at x equals 1, there is a local minimum point. And we can also see the absolute max and minimum values. This is the possible lowest value, right? That's why this is the absolute minimum value of your function. Is there any absolute maximum value? You see your function keeps increasing and increasing towards plus infinity. So no absolute maximum value is attained by this function. Okay, let's move on. And yes, this is the last part of this lecture video. Thank you for your attention.